How is everybody doing today? Hopefully you are doing well. Looks like it's a beautiful day outside. I hope that each of us gets a chance to go outside and maybe enjoy a few moments out there. Office life is the worst, right? Alright, so a couple of announcements before we get started here. This is class 25 and we only get through 38 this semester. So we are really making good progress. But then that also highlights how little time is left and how much we still need to learn. If you look at the course schedule, the updated one that I provided on the 22nd of February after some of the ice storm closures had finalized, you'll notice on that updated schedule that there's less of a gap between submissions in the last part of the semester, where you may have a homework assignment due one day and then the design project due the next, and that is going to be the case on a couple of things where, for instance, homework 8 is due on the 26th. Hold on a second. Yeah, the 20th. I think I messed up this announcement. It's March 26th is the date of Friday. I'm glad I noticed that. So homework 8 due on Friday, just as it says on the course schedule. And then the design project phase 2 is due on Friday the 2nd of April. And I sent an email link out yesterday that has a couple of videos that I've posted on YouTube. One is a Excel-based Hardy Cross solution to a pipe network, and that's just kind of a proof of what the flow rates and the pressures are at junctions. And then the other one, this may be more important to you now since you're working on phase 2 of the project, is an illustration of how to use EPA-NET. And we got some initial exposure to EPA-NET last semester in the fluid mechanics lab, but that was just really rudimentary. And so with this new demo that I've posted, I show you how to do things like make incremental adjustment to pipe diameter and recalculate the pipe network to find out how the pressures have changed and so on. So I really encourage you to look over that video. The demo that I posted yesterday, I think the EPA-NET one is only about 15 minutes long, so it's not too lengthy. Today we're going to continue our discussion of topics from Chapter 12. And that's where we've moved on from steady uniform flow, which Manning's equation can handle. We've moved on to looking at some of the math and some of the fundamental characterizations of energy that will enable us to predict what is the flow depth when we have non-uniform conditions, when we have unsteady flow. So that's Chapter 12. And today, really, we've got a couple of examples. It's like math class today. We're just going to be solving a couple of examples. That's, it's a hydraulics application. But this is the sort of thing where I wish we were in the same room together so that I could do these on the board while you watched and then circulate around and look over your shoulder. Today's lecture, I think, is going to be sort of hampered by the remote environment, but we'll just see what we can do. Remember that in the Excel calculations that were done on Monday's class, we had prepared a figure called an alternate depth graph, a specific energy diagram. And so the specific energy diagram was just for a single flow rate, all the different variety of depths and corresponding flow velocities that could give you that particular flow rate. And so remember, if we are sending 10 cubic meters per second down a rectangular channel that's 4 meters wide, you might have a really steep rectangular channel. And if the channel is really steep, then that 10 cubic meters per second is going to be flowing fast with a high velocity, and therefore the depth would be relatively low. And so that would be on the lower part of this graph, the supercritical zone, where you have a lot of velocity but very little depth. Or at the other end of the spectrum, you may have a relatively mild slope. And so that means that the 10 cubic meters per second is flowing through that channel very slowly, with a low velocity, which means the depth, y, has to be greater. And so then anything above this minima point would be the subcritical zone in the specific energy diagram. And then this dividing line, the minimum specific energy, corresponded to the critical depth. So that's just a refresher of some of the things that we were talking about during our class on Monday. Now here is the formula for specific energy. Specific energy is how much energy is in the water above the channel bed. So we're ignoring any elevation of the channel bed above a datum. We're just looking at using the channel bed itself at a location as our datum. How much energy is in the water at that point? And so it exists as the potential energy, which is the flow depth, and the kinetic energy, which is the velocity head. And velocity head, of course, sometimes is expressed most conveniently as a function of flow rate rather than flow velocity. Okay, now what if our depth on this diagram, what if we have a depth of 0.5? So what we could do is we could go over on the graph using 0.5 as our depth, go over, intercept the figure, and then down to the specific energy. All right, and we could do that by inspection, or we could set up the specific energy diagram according to the same method that had been demonstrated in Monday's class. And we could put in a y of 0.5 and calculate E. But let's use the specific energy equation to find out the alternate depth. Let's do it numerically, because graphically we can find the alternate depth. So graphically, if you go over, follow my cursor here now, if you go sideways and intercept the figure, so here's our specific energy, and then up the same amount of specific energy, and then back over again, it looks like it's maybe about 1.45 or so, approximately. Let's find out exactly the alternate depth corresponding to 0.5. So 0.5 meters is one of the depths for that amount of specific energy. Which is the other? Okay, now the way to do this is we're going to just neglect energy losses. We're going to assume that there's two different depths there, and that if there was a jump between them, that there wouldn't be energy losses in the hydraulic jump. And in future examples we will address how you could account for like the turbulence that exists in a hydraulic jump and how much energy is being dissipated and so on. But let's just find out what is the alternate depth for a depth of 0.5. So the way to do that is we have to find out what is the flow velocity if we have that depth of 0.5, and what is the, well, the depth is already known, so we know y. So find out what is the flow velocity, v, solve for E, and then there's a second depth. And so we might as well just leave this Q as 10 cubic meters per second. So first thing, you solve for what is energy. So substitute Q is 10, square it, 2G A squared. So what is the area of this channel? If the depth is 0.5 and the channel width is 4 and it's rectangular, the area is just going to be 0.5 times 4. So find out first of all what is E. So let me pause for a second and allow you to calculate what is E, what's the magnitude of the specific energy for this depth of 0.5. And then we'll talk about how you can solve for the other depth once you know how much specific energy there is. And by the way, when you've calculated that, please go ahead and type your guess into the chat box, and that way I'll know from a pacing standpoint whether you've been able to calculate the specific energy. Hopefully you got that the the specific energy that's in the channel is 1 point, oh, here we go. It resizes the window when I drag it over from my secondary screen. 1.774 meters. Well, shoot. All right, I'll just do that. Okay, at a depth of 0.5, then that means y is 0.5. The width of the channel is still 4, so the area is going to be b times y. The depth is also here in this first term, so the energy 1.774. So there's another depth out there that gives you the same amount of energy, and we can see it graphically here. So when you've got 1.77, here's the 0.5 that gives you the 1.77. So what is this other depth that gives you the same amount of specific energy? Okay, so what we do is we say 1.774 is equal to y plus q squared divided by 2ga squared. And so q squared is 100 because this is 10 cubic meters per second. 2g down in the denominator, and then a squared. So 4y, and then squaring that. Now we already know that 0.5 will give you a solution. So we already know that root. That's not the root that we're interested in. What we end up with is if you multiply, just combining variables here in the denominator, by the way, so 4 squared is 16 times 2g, and then I want to 100 divided by that gives us 0.3186 in the numerator, and then multiply each term by y squared. So you can see I'm just doing a little bit of algebra rodeo here. On the left side of the equation now, 1.774 y squared. This y has been multiplied by y squared, so now it's y cubed. And then the term furthest most on the right, we multiplied that by y squared, and so now it's out of the denominator. So now this is a cubic equation, and I can rewrite that as y cubed, and then move the minus, subtract the y squared term to the other side, so minus 1.774 y squared plus 0.3186. So on your calculator, can you solve equations like this? On your Casio, I know that I can here on the HP. We're looking for what are the three roots of this equation. We already know one of them is 0.5. You can use solver. The thing about solver is that it's going to require an initial guess. And so if the initial guess that you give it is like 0.4, then it would go out and find whichever solution is closest to that initial guess. So if you told it 0.4 is the initial guess, it's just going to go and find the root that you already know. So solver can work, but then you're going to have to just make sure that the initial guess you give it is like around, is larger. Maybe you want to give the initial guess like 5. And so then as it's zooming back and forth looking for, with a numerical solution, what value of y gives you equality, then it would find the root that you don't know yet. So the other way is just to do the solve for the roots themselves. And so we have one of the solutions at the depth we already know. One of the solutions is a negative value, which doesn't have any meaning when we're talking about a flow depth. But the subcritical root is 1.658 meters. And so we had a supercritical depth and a subcritical depth. And so when you have 1.774 meters of energy, then it can either be a subcritical depth that's causing that, in which case most of the energy is coming from the velocity head, or it could be a subcritical depth where you're having only a small fraction of the energy is from velocity head and the majority of it is from the depth itself. Okay, so does everybody understand this approach here of how to find the alternate depth? What we're trying to do is find out from a numerical standpoint what is that other depth that has the same amount of specific energy. Let me put it back up on the screen here in case anybody wants to ask a question. 1.66 on Casio. Good. All right. Critical conditions is when you have the lowest specific energy for a certain channel and a certain flow rate. So this critical point is the location where you've got the lowest specific energy for a certain flow rate. And what it means is that the amount of specific energy, let's see, one of those equations, the super equation, and one is the sub. Yes. The solution, this is the supercritical depth that solves the equation, and this is the subcritical depth. So what we know is that the critical depth is somewhere in the middle between those two. Not necessarily in the middle, but it's between them. But yes, this is supercritical flow and this is subcritical flow, if the water is those depths. Alright, so critical conditions is what minimizes the amount of specific energy required to convey water through a channel. And here's our formula for specific energy. And if you take the derivative with respect to a change in depth, then what we would get from that is this equation for what is critical conditions. So we're looking for where is it that the flow rate squared times the top width divided by G times A cubed is equal to 1. Because we're getting no change in the specific energy with respect to depth. And the top width, if you do this very small incremental depth, dy, then the top width is equal to the change in cross-sectional area with the change in depth. Because for a very small area, then these the side effects, similar to what I was talking about in Monday's class about how for a very wide channel the hydraulic depth is equal to actually the flow depth. Well, a related thing to that is that the change in area with respect to a change in depth is essentially just the top width B when you have a very thin slice of a cross section, even when that cross section is irregular like this one. So at the margin then, this is how we can determine whether the flow conditions are critical, as we could solve for the flow depth, which goes into A, that would give you 1 on the right-hand side of that equation. This equation is always going to work. I'll show you an equation in a minute that is only applicable for a rectangular channel, but this equation is valid regardless of whether it's trapezoidal, triangular, irregular, whatever the shape. This equation will always, and this is the same thing as this one, BC means the top width when conditions are critical. A sub C means the cross-sectional area when conditions are critical. So this always applies, and let's just find out what depth would give you critical flow when you have a rectangular channel and the same conditions as we've been looking at before. It's this rectangular channel that has a width of 4 meters and a flow rate of 10 cubic meters per second. So if we go back to the figure, we're trying to find out what is the critical depth. So just by looking at it, it's maybe around 0.9 approximately. But let's solve for it using the formula. Here. So Q squared, so that'll be 100 in the numerator on the left side. G is 9.81. BC is 4. And then the area, when conditions are critical, is 4, which is the width, multiplied by y cubed. Y sub c cubed, so the critical depth cubed. Let me give you a moment to jot that down and try and solve for what is the depth when conditions are critical. Okay, on the left-hand side of the equation we've got Q squared, so that is going to be 100 divided by G, which is 9.81. On the right-hand side of the equation is 4, which is the top width, times YC, and then that's cubed. And then in the denominator of the right-hand side of the equation is the width of the channel, B sub c. Here in my equation I'm saying T sub c. That's just the top width. That's a variable that's used in place of capital B in some texts, but we're going to substitute in 4 there as well. So I've rearranged symbolically for y sub c, and we get that the depth should be 0.860 meters. So that's the critical depth. And that formula can apply whether the shape of the channel is rectangular, trapezoidal. It's always valid. So you need to be careful, because this version of the equation will give you the critical depth only if the channel is rectangular. And it relies on a parameter known as flow per unit width. So you can calculate a flow per unit width if you have a rectangular channel. And so when the channel is rectangular, the top width, capital B, is the same as the bottom width, lowercase b. And so flow per unit width is the flow rate, capital Q, so that would be cubic meters per second, divided by the channel width, lowercase b. And so this flow per unit width is going to be, think about the units, it's either cubic meters per second per meter of width, or the other way to think about it is as meter squared per second when the units cancel. Okay, so this same channel, the same rectangular channel that we already found from the previous example using this formula, we found that the critical depth is 0.860. Let's double check this formula, which only works for a rectangular channel. And so first of all, calculate the flow per unit width, lowercase q. So our flow rate is 10, and the channel width is 4. So lowercase q should be 2.5 meters squared per second. And then here in the formula you square that. Okay, so I'm now 2.5 times 2.5 in the numerator, and now divide by g, so divided by 9.81. And then finally we take that to the cubed, to the 1/3 power. So it's important to pay note of the exponents here. One of the common mistakes I see on exams and homework assignments is that people forget to square the flow per unit width inside, and then they forget to take the to the 1/3 power once the ratio has been calculated. So just to refresh, we had done flow per unit width, which is 2.5, squared it, and then divide by 9.81. Okay, so that's 0.637, and then that needs to be to the power of 1/3, so to the power of 0.33333. Okay, and here again we have 0.860. So you can find the flow per unit width, square that, divide it by g, and all of it to the 1/3 power, and it gives you the same 0.860 critical depth. So what is critical depth? That's the depth that conveys the water through the channel with the least amount of specific energy. And the reason why you need to know that is that there are going to be times when the water is trying to get over some obstacle. And the water, now of course the water isn't conscious, and so if I slip up and I try and say that the water is trying to do something, I don't mean that it's making the conscious decision to overcome an obstacle. What I mean is that the energy in the system is building until there's a reaction to a certain amount of accumulated energy. And so when there's an obstruction in the channel, the water will try and flow over the obstruction, and it may require that the water level rises until there's enough energy to flow over the top of the obstruction. And when it does, the water will flow over the top of the obstruction at the critical depth. So that's why we have to know about the critical depth, is that oftentimes there are going to be, whether it's a change in channel width or whether it's a step up in the bottom bed, there are going to be these things that causes the water to flow at the critical depth. And so you'll need to, it does have physical significance. It's not just some abstract notion of a depth that exists only on a chart. It does have physical meaning. Okay, so our last example for today, we've got a trapezoidal channel, 186 cubic meters per second going through that trapezoidal channel. You can see I've copied the parameters here for the top width, the parameter for the cross-sectional area, wetted perimeter, and then the side slope. Since this is 1.5 horizontal for every 1 vertical, then that means that T is 1.5. All right, I'm asking you to calculate the critical slope. And what critical slope is, it is the slope that will cause the critical depth. And so this is a two-part problem. The first thing you need to do is calculate what is the critical depth. And you use this formula to do that. So part 1 in your notes, in the margin of what you printed out there, this is a two-part problem. Part 1, find critical depth, y sub c. So use this formula to solve for y sub c. So what you're going to substitute into this formula is b. So here's a capital B in the formula, right? So you're going to put lowercase b plus 2ty. Y is unknown. So the y that you're solving for is you're solving for the critical depth, y sub c. Now this is equal to 1, which is that's true when conditions are critical. In the denominator here, g is a constant, but then a, here's the formula for a, it's going to be a function of the unknown depth, y sub c. So we've got y in the numerator and in the denominator. So you can either solve that numerically with Excel, you know, where you keep changing around and playing with values of y until you found on the left-hand side that depth y that gives you it equal to 1. Or you can set it up, you know, once you've written it out on paper, you can set it up in your solver and solve for the critical depth. So that's part 1, find the critical depth. Part 2 is now insert the critical depth into Manning's equation along with the n value for this concrete channel, along with the flow rate of 186. And this time what we're solving for is the slope, s. We haven't done that before. Sometimes I've asked you to solve for Q, and sometimes I've asked you to solve for the depth. But now both of those parameters are given, and what we're asking is how steep should the channel be to cause the critical depth. Okay, I'm going to put you into the breakout groups just in case if you're confused about how to do this, you can ask a classmate. All right, what are B and T again? So B is the bottom width. So B is 3. So in this trapezoidal channel, the bottom width is 3 meters. So that's lowercase b. And then T is referring to the side slope. And so let me take you back to some formulas I've showed you before. Here they are. So that's saying for every 1 unit of vertical, you've got T units of horizontal. So vertical 1, T horizontal. So what that says for this one then, all right, so in this diagram, we've got, it's saying 1.5 horizontal to 1 vertical. So that means T is 1.5. Okay, 2 steps. Find y sub c, then find the slope. I'll put you in the breakout room so you can chat amongst yourselves. We've got about 10, 12 minutes that you can spend on this 2-part problem, and then we'll reassemble to look over the solution together. First of all, find the critical depth. So substituting in the flow rate squared, and then you know, our expressions for this channel that has a bottom width of 3 meters and 1.5 horizontal to 1 vertical. So that means the W term that's going to go in our geometric parameters is 1.803. Okay, so looks like maybe I didn't even end up using that. I'm going with just the rectangle, and then the side triangles put together as another rectangle. In any case, the critical depth is 4.12, and then once you know that, you can substitute it into the formula for area and wetted perimeter, because hydraulic radius, remember, is area divided by wetted perimeter. So Manning's equation is area divided by n times the hydraulic radius to the 2/3 power divided by slope to the 1/2. So rearranging that equation, we're going to want to solve for the critical slope. Okay, so got the depth, and the wetted perimeter that goes along with that depth is 17.86 meters. The cross-sectional area that goes along with that depth is 37.84 meters squared. And then I rearranged Manning's equation to solve for the slope. Okay, so in the numerator is the Manning's n 0.013, the flow rate 186, then the denominator area times the hydraulic radius to the 2/3 power, where hydraulic radius is area divided by wetted perimeter. Okay, so the slope that you'll solve for there should be about 0.0015. So that's the critical slope. So if you have a trapezoidal channel and you want the flow to be critical, then it should be laid out on that 0.15% slope. And that is where we leave it for today. Reminder that your homework assignment 8 is due on Friday. So let me just pull that up real quick. Refamiliarize myself with what that assignment looks like. Homework 8. All right. So find the flow depth. Looks like I'm telling you the flow rate Q, the geometry, the side slopes, and so on. Here is a Manning's equation problem. And I'm giving it to you in traditional units, and I've even given you this hint. Remember, you have to use the 1.86 coefficient on the front when you're using Manning's equation. Here's another Manning's equation where solve for the flow depth. Determine the flow depth. We've got trapezoidal channel and Manning's equation. Trapezoidal channel, this time traditional units, and what slope. So solving for the slope when you want a certain amount of shear stress not to be exceeded. And then a couple of textbook problems, including some that begin with chapter 12, so like specific energy type questions. So this one's 10 problems. That assignment is due on Friday, and it should be uploaded to Blackboard before 1 o'clock as usual. So if you have any questions on the assignment, feel free to give me a call on Teams. You know, nobody's done that this whole semester, I don't think. Not a single person has called me on Teams, which is a pity because that's such a convenient way to get in touch. But email's also okay. I'd be glad to hear from you. That's all for today. So I'll see you on Friday. Take care, everybody.